This is a Love at Physics video about converting AC to DC and rectification. Now we've seen that AC is delivered to our homes, and the reason that we use AC for most long distance energy transmission throughout the world is because it can be very, very easily stepped up and stepped down using transformers. Transformers are very good because they make it very easy to increase the voltage and decrease the current while you're transmitting electrical power across large distances. So the transformers enable us to transfer electricity a long way without very much energy loss. DC, that can be done as well, and there are certain projects, particularly in South America, that use long distance DC transmission using a high voltage and low current, but the system to change the voltage and the current is not as simple as transformers, so most of the world uses AC. So when we get AC delivered to our homes, why do we even need to bother with DC? We've got AC electricity, it's very easy to step up and step down. Why bother with DC? Well, we didn't used to bother very much with DC when we first started distributing energy with AC. AC is very useful in things like light bulbs, old-fashioned radios, old-fashioned fridges and kitchen equipment, and they worked very well with AC. However, with the new technology generation, we have things that use semiconductors. Now, semiconductors are in every single computer chip, and semiconductors can only use DC to operate. We have to have DC to use a semiconductor. So anything with a chip in it, a computer chip of any sort, any of these things all need DC. So we need to be able to convert from AC to DC when the electricity gets to our home. Now, the way that we convert from AC to DC is we use a rectifier, and there are lots of different sorts of rectifiers that we can use. Now, three that we're going to focus on in this video are half-wave and full-wave rectifiers using diodes and then also adding in capacitors. So a diode is an electrical component which only allows current to flow in one direction. So this is the negative side and this is the positive side. So conventional current can only flow in one direction. That's fine, and so what that means is if we have an AC supply and then we put a diode in there and then we have an output here, what that's going to mean is we go from the AC current like that, and then the diode only lets the current flow in one direction, so we get rid of this bit and we get rid of this bit because the current can't flow that direction, so our output wave looks something like that. And that, because you get half the wave, is called a half-wave rectifier. Now, if we want to be slightly more advanced than a half-wave rectifier, we can use one of these. Now, this is just 4 diodes connected in a diamond shape, and you can see that all the diodes are pointing that way. What that means is when you get your AC circuit coming in at the top, if the AC is positive, then it makes this positive, but if the AC is negative, then it also makes this side positive, and I'll show you an animation in a second just to show you that. But what you end up with is this always being positive, this always being negative, and the output wave turns both positive and negative parts of the AC. If this is the original AC, both positive and negative parts turn into positive parts of the wave. So you get this kind of lumpy effect on the wave. Now that is called full wave rectification. A full wave rectifier. And this diamond formation is called a diode bridge. So that is a diode bridge circuit, and that is a full wave rectifier, so it gives you this. So we're getting closer to DC, but DC is a constant output current, not just a positive one that bounces along like that. So we need to move on a little bit. But before we move on, I'm just going to show you an animation which shows you this relationship and the input and output of the diode bridge. Now this animation shows you a diode bridge circuit, and the red line is positive, and so you can see that the AC will alternate between positive and negative, and the way that that positive charge is distributed by those diodes depends on which side of the AC happens to be positive at that time. So if I pause it here, then the positive travels through this diode and it makes the top of the DC positive. And then if we play it again and pause it there, then the positive is at the bottom here and it travels through this diode and makes the top positive. Just the same as the negative here travels this way, and the negative, if it comes this way, the negative travels this way. So the bottom half of the DC there is always negative and the top half is always positive. So that is going to give us this shape graph with that diode bridge. Now obviously that isn't a perfect DC signal, but it's getting there. The way that we make it even better is by adding a capacitor. Now a capacitor you will study in 11.3, but a capacitor is basically a mini battery. It stores charge for a certain amount of time, but that amount of time is generally quite short, and the capacitor can be put in series here, and what it does is when we have the peak here, then the capacitor gets charged up, and as the voltage drops coming out of the diodes, as the voltage drops, the capacitor starts to discharge and it kind of fills those gaps, so you get this kind of a shape, which is getting closer and closer to that solid DC current that we're after. So you could use a half wave rectifier, which is a single diode. You could use a full wave rectifier using a diode bridge, and you can add a capacitor in to start to flatten that out. Now the higher the capacitor, the higher the capacitance of this capacitor, the flatter it gets and the smaller this ripple effect becomes. That was a Love at Physics video about converting AC to DC for IB level students. If you liked the video, please hit like. Feel free to ask any questions in the comments below, and if you want me to make some more, please subscribe. Thanks very much.